Alright, so what we're going to be doing today is solving the pendulum equation, the simple pendulum equation, in 7 different ways. So get lit. Alright, so first the derivation using Newton's second law. So here we have a pendulum on a rod of length L, which is massless and rigid. The usual assumptions have mass m hanging on the end. This point is fixed, and we have an acceleration due to gravity, g, in the downward direction here. So how do we solve this? Well, if we draw a free body diagram with this mass here, then there's only going to be one force that we're considering, and that's the force of gravity, and we know it's going to be down with the strength m times g, the acceleration due to gravity. Now we want to resolve this force into several components. So we're going to introduce an angle with the vertical, theta, and we want to figure out the radial portion of the force, and we want to figure out the tangential portion of the force. So there's going to be one of each. So tangential is going to be F sub theta is what I'm going to call it, and F sub r is going to be the force in the radial direction. And what you'll notice first of all is that the force in the radial direction has got to be balanced by the normal force, because this thing is constrained. It cannot move in at all. This rod is not compressible or stretchable, if you like. It's not elastic. So there's got to be a normal force going in exactly the negative radial direction, and we have to have F sub n is equal to, in magnitude, F sub r. So really all we're interested in is the tangential component of the force. So it should be fairly obvious, if you've ever done these sort of problems before, that the radial force and the tangential force are both going to be something like mg cosine theta and mg sine theta. But we don't know which is which at first. So what we could do to do this is look as theta approaches 0, the limit from above, then the force of gravity is going to become a strictly radial force. So we want the one that's not going to vanish to be the radial force. So this is going to be Fr, and then this is going to have to be, by process of elimination, F theta. As we go, theta is 90 degrees exactly. The force of gravity is going to be exactly in this direction, but if we're using the normal counterclockwise convention, we're going to have that this is equal to negative mg sine theta times theta hat, right? So if we have theta hat in this direction and r hat in that direction, then we're going to have something like this. Okay, since the normal force balances the radial force, this is just going to be equal to the negative of the normal force, and that part is all solved and figured out. That doesn't pertain at all to the motion. We're only interested in the radial component here. So what do? We write F equals ma in classic fashion. F is going to be equal to this force, obviously, so we're going to have F equals ma implies negative mg sine theta is going to be equal to ma. Now what is a here? It's not going to be a normal acceleration. So an arc length acceleration, if you will, is going to be, we'll call S arc length, is going to be equal to L times theta, right? Now, so if L is constant and S and theta are functions of time, then S dot is equal to L theta dot, and S double dot is equal to L theta double dot, which means we are going to get that this is equal to ML theta double dot. Now, if we divide by M, which is non-zero, And then we can write on the same side theta double dot plus g over L times sine theta is equal to 0. This is our nonlinear pendulum equation. For the moment, let's think, can we linearize this? And what do we need to do in order to linearize? We need to look locally about some location. And so we're going to want to consider just small oscillations, right? So tiny little angles, or theta way less than 1 if you like, in which case we can expand sine theta into its Taylor series, which should look something like theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus etc. And we notice that for increasingly small theta, this is the leading term, so that up to a fairly good approximation, and it is certainly true in the limiting case, sine theta is approximately equal to theta. And again, I want to make it very clear that this is for theta much less than 1. So if we replace sine theta by theta here, we get the equation theta double dot plus g over L times theta is equal to 0. And theta is, of course, a function of time, t. All right, so method 1 is going to be dimensional analysis. Maybe not really an analytical technique, but it's extremely useful and extremely important to physical reasoning. So, what are our parameters? They're going to be theta, which is dimensionless, radians. We're going to have mass, which has the units of, well, mass. We're going to have L, which is length, right? We're going to have T, which has units of time. Fairly straightforward so far. And we're going to have g, which is an acceleration due to gravity, which means that its units are going to be length divided by time squared. All right, these are all the parameters we could possibly need in our solution. What we're going to want to do is figure out all possible combinations of these parameters which allow you to create dimensionless constants. So, there's really only going to be one here, and that's going to be, consider g for a second. What would we have to multiply by g in order to get something dimensionless? Well, we'd have to multiply by time squared, so g t squared, and then we'd have to divide by length, so over L. And this is going to be our only dimensionless group. So that we know that if theta is a dimensionless dependent variable, we know that it's going to be a function of some dimensionless group. And since there's only one dimensionless group here, we know that theta, as a function of time, is also going to be an explicit function of g t squared over L. And this does turn out to be correct. All right, now if we take a look at this arbitrary function f, it is a function of t squared. But we're not really interested in knowing the angle as a function of t squared. We're interested in knowing it as a function of t, right? So because f is arbitrary, we can just say, well, it's equal to some other arbitrary function squared, where h is going to be a function of root g over L times t. Now it's very clear that the square root of g over L is going to be the frequency of a periodic function h. Right? These have to be periodic. F has to be periodic in t squared, h has to be periodic in t, and the reason is that we're going to have oscillating motion, right? We want it to go back and forth, so clearly it's going to be some periodic function of time, the angle is. With that in mind, we have a frequency of root g over L, and of course, the period of such a hypothetical function is going to be equal to 1 over the frequency, which is going to be the square root of L over g. So that as the pendulum rod, if you like, length gets longer, it's going to have a longer and longer period, right? This is exactly what we'd expect. All right, what's the simplest periodic function we know? Well, sine or cosine. Either one works. so that we know that our function theta as a function of time is going to be something like the sine of our frequency times time, root g over L times t, plus some initial angle. We'll just call it phi naught. And this is basically our solution. You can put an amplitude out front here, but this is basically our solution to the pendulum equation. All right, the second method is going to be basically solution by guessing or by inspection. So if we have theta double dot plus g over L theta is equal to 0, we can instead write this as theta double dot is equal to negative g over L theta, where this is just some positive number so that we can write it alpha, and alpha is greater than 0. So this is kind of what we're looking at, is the second derivative is proportional to the negative of the function. Now what does that actually mean? Well, suppose we drew a graph here. This is t, and this is going to be theta as a function of t. So this means that if we have our function positive, right? If our function is up here, then its concavity has to be negative, so it has to look like that. Now, suppose at some later time it crosses the time axis and it's negative. Well, then it's going to have a positive concavity. And if it has a positive concavity, it's obviously eventually going to intersect again with the axis, which means it's going to have to turn around again, and so on. And this is starting to look very familiar. This is going to be none other than a sine wave, right? Just by inspection, you can tell what function satisfies this property, that if you take a derivative twice, you get back the negative of that function, or proportional to the negative of that function. And it's true, the only functions that have this property are going to be sine and cosine. But of course, we've got to get this negative alpha back. And so the trick with that is going to be, recall the chain rule, where you take the derivative with respect to time of, say, sine omega t. Well, this is going to be omega times cosine omega t. So that if you do it twice, you'll get back sine omega t again, multiplied by a negative sign and by omega squared. So we need our omega squared to equal to alpha, so that the answer is going to end up being sine of the square root of alpha, or in our case, the square root of g over L times t. And of course, sine would work too, and because it's a second order linear equation, we actually need two linearly independent solutions, so multiply that by an arbitrary constant, or and then add this to cosine root g over L t. And of course, you could instead have this you could have it phase shifted. So sine of root g over L t plus some phi naught times a constant, and it's going to be the same story. So our second solution, or method of solution, is just going to be by looking at it and thinking, that's the only function that could possibly satisfy that. Alright, so now we're going to get a little bit more sophisticated, and we're going to use complex exponentials. So let's assume theta as a function of t is equal to e to the ct, where c is just some complex number in general. Alright, so if we take a derivative, we're going to get c e to the ct. And if we take two derivatives, this is just going to be c squared times e to the ct. Alright. So we know that our theta must satisfy theta double dot plus g over L theta is equal to 0, or this is equal to negative g over L theta, right? So that if we substitute these, we get c squared e to the ct is equal to negative g over L times e to the ct. The only way that this could be satisfied is if c squared is equal to negative g over L. So if we take the square roots, we're going to get two of them, and since g over L is a positive real number, we're going to get c is going to equal to plus or minus I, the square root of negative 1, times square root of g over L. So these are going to be our two c values. If we then substitute that into here, we get one solution, theta 1, is going to be equal to e to the c1t is going to be equal to e to the I root g over L t, which by Euler's formula is going to be cosine of root g over L t plus I sine root g over L t. All right, then our second solution is just going to be e to the negative I root g over L t, and that's going to give us theta 2 is equal to cosine of this minus I sine of that. And we're only actually interested in real valued solutions, so when we pick our, in general, complex coefficients out front, we're going to make sure that they cancel out in just the right way, so that we get theta is the sum of two linearly independent solutions, and you're going to get equals C1, if you will, cosine of root g over L t plus C2 times sine of root g over L t. Where, of course, we could also put this in the phase shift form. Method 4, now things are getting kind of spicy. Let's use the Laplace transform. So the Laplace transform, if you'll recall, of a function of, say, t is defined to be the integral from 0 to infinity of f of t e to the negative st dt, where s is a complex number with real part greater than 0. So we want to take this integral. So if we have the Laplace transform of theta dot, or rather theta double dot, is what we're interested in. So this is going to be equal to theta double dot e of t, well, just to be clear, e to the negative st dt. And if we integrate this by parts, we're going to get theta dot e to the negative st evaluated at 0 to infinity, minus times the derivative of negative s comes down, so you're going to have plus s out front, e to the negative st dt. Integrate by parts again, theta dot e to the negative st 0 to infinity, plus s times theta e to the negative st evaluated at 0 to infinity minus integral from 0 to infinity, and you're going to get that same negative s again, so that we get theta e to the negative st dt. And of course this integral is just the Laplace transform of the function theta, so that we get, notice that as the exponential, because the real part of s is greater than 0, it's positive. As t goes to infinity, this is going to become 0, so we don't have to worry about that. And then at 0, that is going to just become 1, and we're going to want theta dot of 0. So this is going to be equal to negative theta dot of 0 plus s times, and here we're going to have similar situation. So negative theta of 0, and then plus s times the Laplace transform of theta. Or we can write this as s squared Laplace transform of theta minus s times theta of 0 minus theta dot of 0. This is what the Laplace transform of the second derivative is. So then we're going to use this to take the Laplace transform of our entire differential equation, solve it for the Laplace transform, and then invert. So let's do that. Alright, so I just wrote what we figured out and our differential equation right here. Let's take the Laplace transform of both sides. Well, if we do this, well, the Laplace transform of 0 is just going to be 0, right? And The Laplace transform is a linear operator, which means this is equal to the Laplace transform of theta double dot plus g over L times Laplace transform of theta. But we have an expression for this, right? It's up here. So that means that s squared Laplace transform of theta minus s theta of 0 minus theta dot of 0 plus g over L Laplace transform of theta is equal to 0. All right, now we're going to collect terms. So Laplace transform of theta times s squared and plus g over L. Plus g over L. And then we're going to move the other stuff to the other side. So this is going to be equal to theta of 0 times s plus theta dot of 0. All right, now we're going to divide by s squared plus g over L, and we're going to get that the Laplace transform of theta of t is going to be equal to theta of 0 times s over s squared plus g over L plus theta dot of 0 times 1 over s squared plus g over L. The reason I've written it this way is that this is just a constant times a familiar Laplace transform plus another constant times a familiar Laplace transform. So now I'm just going to call this C1 because it's an arbitrary constant, and I'm going to call this C2 because it's another arbitrary constant. Now these are both familiar, and so we can write this as C1 times the Laplace transform of none other than cosine of root g over L times t. It's whatever square root of this is, right? We'd have a squared constant in the bottom, plus C2 times the Laplace transform of sine of root g over L t. But since the Laplace transform is a linear operator, we can rewrite this as Laplace transform of C1 of cosine root g over Lt plus C2 sine of root g over Lt. And then if we have the Laplace transform of two functions are equal, then the two functions must be equal, so that we have theta as a function of time is none other than some arbitrary constant of time, or times cosine of root g for Lt plus another arbitrary constant times that. And we get our answer again. We're going to build on our approach from before using dimensional analysis. So if we want to expand theta in a Taylor series, well, function of time is not going to work so hot because you're going to have time plus time squared plus time cubed, and that's not going to be okay. So we're going to want to make this equation dimensionless. So what we're going to do is make a substitution. So let's set tau equal to time over the period capital T. If we do this, we're going to get that the derivative of theta with respect to tau is going to be equal to the derivative of theta with respect to t times the derivative of t with respect to tau, right? This is just the chain rule. And the derivative of t with respect to tau is just going to be equal to capital T. So if we take a second derivative then, this is going to be t squared. Another factor is going to come out. So that if we divide, we get 1 over the period squared times second derivative with respect to tau is equal to the second derivative with respect to time t. So that if we substitute this into our equation, what do we get? Well, theta double dot is going to become 1 over t squared, d squared theta d tau squared, plus g over L times just theta is equal to 0. Now this, I claim, is a dimensionless equation because if we multiply through by t squared, we will get plus t squared g over L. And if you recall, g over L is going to have units of length per time squared times 1 over length, right? So it's just going to be 1 over time squared. So that if you multiply by the period squared, which has units time squared, you're going to get something which is dimensionless. So this we can just call a constant. We will call it, well, we can call it whatever we want. It's an arbitrary constant, although we found out before that t, the period, the only way that we can even get a period is if it's square root of L over G. So what happens is they actually cancel each other out and you get just equal to 1. And then we can make our substitution again later. Alright, so let's solve this equation by expanding theta in a Taylor series in the variable tau. Alright, so first we're going to suppose that theta is an analytic function so that it can be written as a power series where tau is our independent variable and the a sub n are just coefficients, right? And what we're hoping to do in order to solve for theta is to figure out what these coefficients are. Alright, so if we take the derivative of this, I'm going to use dot to mean derivative with respect to tau now, not t. So theta dot is going to be equal to sum from 0 to infinity of the n comes down, and we get that, right? So theta double dot is going to be sum from n equals 0 to infinity of likewise n minus 1 times n a sub n tau to the n minus 2, right? This is just term by term differentiation. So now what we want to do is look at the n equals 0 value. Well, if you plug n equals 0 into this, notice that there's an n, so this will just be 0. So we could start at 1. Well, but if you plug 1 in, you'll also get 0, so we could actually just start at 2. Alright, but I actually want to start at 0. I'll make up your mind, Ben. Well, we can move the index down to 0. And what's that going to do? If we shift this down, then for everything else to keep its value, it has to go up by 2. So this is going to be n plus 2, n plus 1, a sub n plus 2, tau to the n. Alright, why I did this will be clear in a sec. So now let's write our differential equation in terms of these power series. So theta double dot plus theta is equal to 0, right? So this says that the series n is equal to 0 to infinity of n plus 2, n plus 1, a sub n plus 2, tau to the n, plus the sum from n equals 0 to infinity of, what was our original one? A sub n tau to the n is equal to 0. Now, because these have the same index, right, they go from 0 to infinity, and they're both to this, multiplying the same power of tau for each term, we can combine them into one infinite series so that we have sum from n equals 0 to infinity, and I'm going to factor out the tau to the n, and then we'll have multiplying that n plus 2, n plus 1, a sub n plus 2, plus a sub n. And if this has to be 0 for every single term, then, and this is true for whatever tau value we choose, then it must be true that these coefficients are 0. So we're going to set this identically equal to 0, and then solve for a sub n plus 2 in terms of a sub n, giving us a recurrence relation. Alright, so I wrote our relation up here, and now we'd like to solve for a sub n plus 2. So we just move a sub n over, divide, and we get a sub n plus 2 is equal to negative a sub n all over n plus 1, n plus 2. This means that, for instance, a sub 2 is going to be equal to negative a sub 0 over, well, what's 0 plus 1 and 0 plus 2? This is going to be 1 times 2. And likewise, a sub 4 is going to be equal to negative negative a sub 2 all over 3 times 4. But we already have a formula for a sub 2, and that's going to be negative 1 squared times a naught all over 1 times 2 times 3 times 4. Very quickly, we see that this is going to form a pattern. And the general pattern is that for our even numbers, we're going to have a sub 2k is equal to a naught times negative 1 to the k all over 2k factorial. This is very easy to verify. Likewise, with the odd numbered terms, if we start with a sub 1, we're going to have a sub 3 is equal to negative a sub 1 all over 2 times 3. And a sub 5 is equal to negative a sub 3 over 4 times 5. But we have an expression for that already, is equal to a sub 1 times negative 1 squared all over 1 times 2 times 3 times 4 times 5, right? And so likewise, just as we got this formula, we're going to get a formula for the odd a's in terms of a1, and that's going to be a1 times negative 1 to the k all over 2k plus 1 factorial. Now recall what this means for our series. This means that we have essentially figured out what these coefficients are, but we figured them out in terms of evens and odds. So let's split this power series up into two power series indexed by k. So there's going to be sum from k equals 0 to infinity of a sub 2k times tau to the 2k, right? Plus the sum from k equals 0 to infinity of a sub 2k plus 1, the odd terms, times tau to the 2k plus 1. Alright, so now we substitute our expressions we found for a sub 2k and a sub 2k plus 1. This gives us sum from k equals 0 to infinity of a naught times negative 1 to the k, and we're going to have tau to the 2k all over 2k factorial. Likewise with the second series, we're going to have a 1 times negative 1 to the k times tau to the 2k plus 1 all over 2k plus 1 factorial. Now, because a0 and a1 are just constants, arbitrary constants in fact, we can move them outside of the sums. And now, these expressions should look fairly familiar. These are none other than the Taylor series, or Maclaurin series rather, for sine and cosine. What do you know? So we have equals a0 times the cosine of tau plus a1 times the sine of tau. Right? Now what we can do, if we want theta in terms of t, we can reverse our substitution. So we said that tau is going to be equal to t over the period, where the period was square root of L over G. This means that tau is equal to root G over L, so that flipped, times t. This means that theta as a function of t is equal to an arbitrary constant a0 times the cosine of the square root of G over L times t plus another arbitrary constant times the sine of root G over L times t. And we have our answer. I will warn you that if you use this method, always make sure that your equation is dimensionless ahead of time, so that you don't try to expand in a Taylor series where your variable here has dimensions, because that's not going to make sense. Alright, I am again going to use the dimensionless equation because it's much easier to work with. Theta double dot plus theta is equal to 0. And we should feel fairly justified in doing this, because we can just make a substitution in terms of the period. So, but now let's try something a little bit trickier. So let's multiply this whole equation by 2 times theta dot. You'll see why in a second. And let's actually move this over here. So this is equal to negative theta. So what we're going to have is 2 theta dot theta double dot is equal to negative 2 theta theta dot. But both sides are familiar derivatives, because if you had theta dot squared, then by the chain rule, if you take the derivative of that with respect to time or whatever, I guess it's dimensionless, so tau if you like, it's going to be equal to 2 times theta dot times, by the chain rule, theta double dot, right? And likewise on this side. This means that what we really have is the derivative with respect to tau of theta dot squared equals the derivative with respect to tau of negative theta squared. Now, if we have two things which have the same derivative, then they can only differ by a constant, so that we have theta dot squared has to be equal to negative theta squared plus some constant. We'll call it c for now. All right. Now in the phase plane, this should be very clear that the graph of this would be a circle, right? If we had theta on this axis and theta dot, then the sum of their squares is equal to a constant. Clearly this is going to be a circle, and you're going to have a circular orbit. And the only functions which do this are sine and cosine, but just for kicks, let's do it analytically. So theta dot is going to have to be equal to the square root of, and I'm going to make a substitution here and call this k squared instead of c. It's just an arbitrary number, so it doesn't matter what I call it. K squared minus theta squared. So now I want to take d theta over square root of k squared minus theta squared is equal to dt. We split up the differentials. This is okay in some cases. We integrate both sides, and what we're going to get roughly is that the integral of d theta over square root of k squared minus theta squared is equal to t plus some other constant, let's call it epsilon. And this we can write instead as theta over k squared, 1 minus that, or no, let's leave it as is, k squared minus theta squared, and then let's just make a substitution. Theta is equal to k times, let's say, sine of x. So then we get d theta is equal to k cosine x dx, and our integral becomes k cosine x dx all over the square root of k squared minus k squared sine squared of x. And then, of course, we can factor that out, and we get 1 minus sine squared, which is just going to be cosine squared. So we'll have k squared cosine squared. You take the square root, that's just going to be k cosine. And look, we have magic cancellation here. It's just going to be equal to x, where we already have our arbitrary constant over here. So we can just write x is equal to t plus epsilon. Now what was x exactly? We set x, it'd be theta divided by k sine inverse. So x is equal to sine inverse of theta over k, some constant k, is equal to t plus epsilon. So then we have that theta divided by k is equal to sine of t plus epsilon. And so that if we multiply by k, we get some amplitude. So we now have theta as a function of t. And our two arbitrary constants are k and epsilon. And if we want to get this in the right units, we just make our dimensionless equation dimensional again by the inverse transformation. T is equal to this should be tau, sorry. Tau, if we're doing our convention from earlier. Well, you get the idea. So t is equal to the period times tau is the square root of L over G, so that tau is equal to square root of G over L T. And so we get that this is square root of G over L T plus epsilon, with epsilon and k are arbitrary constants, and this is, of course, exactly true. It's already put in phase amplitude form. So there you have it. Pretty cool. All right, for our final method, we're going to solve this as a system of differential equations. So let's call x is equal to theta, and let's call y is equal to x dot is equal to theta dot, if you will. All right, so what we get then is a system, right? So theta dot is equal to, or theta double dot is equal to negative g over L theta. This implies that that we have a system x dot is equal to y, and y dot, which is theta double dot, is equal to negative g over L times what's theta? X. Or if we want to write this in matrix form, which is going to be convenient for us, we can write it as x dot y dot is equal to 0, 1, negative g over L, 0 times the vector x, y. And then we can solve via eigenvectors. Let's do it. All right, so the first thing we have to do is find the eigenvalues of this matrix, and the way we're going to do this is by taking the determinant negative lambda, 1, negative g over L, negative lambda, and then setting that equal to 0, so that we get lambda squared minus a minus is plus g over L is equal to 0, and this has solutions. Lambda is equal to plus or minus I times the square root of g over L. These are going to be our two eigenvalues. Now let's find the eigenvectors corresponding to them. Alright, so if we plug in the positive eigenvalue, we get minus I root g over L, 1 negative g over L minus I root g over L times xy is equal to 0. Right? This is the 0 vector, rather. And because this is linearly dependent, we only really need one statement, so it's going to be negative I root g over L x plus y is equal to 0. That's just the top row. And we could write this instead as y is equal to I root g over L x, so that if we choose x to be 1, we get an eigenvector, which is 1 I root g over L. Okay, now let's find the other eigenvector. So if we choose this to be the negative value, then minus a minus is a plus, so this will be plus, plus, and we're going to get the same situation. It's pretty simple here, so that we get y is equal to negative root g over Lx, and this is going to give us our second eigenvector, which is going to be 1 negative I root g over L. So we have two complex eigenvectors corresponding to two complex, or really imaginary, eigenvalues. So we're also later going to want to consider complex coefficients so that we resolve everything to get real answers in the end. Alright, so the solution of this is going to be an arbitrary constant times our exponential of t times our first eigenvalue, and this scaling our first eigenvector, and likewise second eigenvalue and second eigenvector. So that we'll get a general solution of C1 times e to the I root g over L t times 1 I root g over L plus C2 e to the negative I root g over L t times 1 negative I root g over L. This is going to be our general solution for this system. Oh, this should be x and y, not x dot and y dot. So that we're only really interested in x, right? Because x we said was equal to theta. Not really interested in solving explicitly for theta dot. Oh, maybe you are, but I'm not. So we only need to take the top row here, and then we want to recall Euler's formula, which allows us to be turned from the complex exponential into a cosine plus a sine of argument root g over L t, just like before. And we want to choose our constants wisely so that we get real answers. And in general, because of linear independence, this is going to end up being cosine of this times, we'll say d1 plus d2, these are real numbers, sine of root g over L t, has theta of t, via matrices and eigenvectors.